Web 3.0 is an unstoppable force coming for every aspect of the internet as we know it. We're seeing new blockchain-based applications pop up for pretty much every internet use case you can think of. And one particular area of the web that's prime for disruption is social media. And so today you're going to learn how to create a blockchain-based social media application just like Twitter, completely powered by Web 3.0 step by step. This is the perfect project if you're trying to learn the fundamentals of blockchain development, how smart contracts work, how NFTs work, and also to use for your portfolio if you're trying to land a highly paid Web 3.0 job. So you don't have to be an expert to get started today. You're going to learn the programming languages, skills, and technologies as you go, how to create the smart contracts with Solidity, how to write the test, how to make a website, and how to put it on the blockchain. So I'm super excited for you to learn this today. So if you're new around here, hey, I'm Gregory, and on this channel, I turn you into a blockchain master. So if that's something that you're interested in, then smash that like button down below for the YouTube algorithm and subscribe to this channel. And if you want to learn how to master blockchain step by step, start to finish, then head on over to dappuniversity.com/bootcamp to get started today. And if you have been watching this channel for a while, then I want to introduce you to our guest presenter today. This is going to be Ethan, who has helped me make this tutorial. He's a total expert in this topic, and he's going to walk you through the entire process step by step from start to finish. So let's jump in and get started.
In this video, I'm going to show you how to build an NFT-based social network, a decentralized version of Twitter. To participate in the network, you have to mint an NFT that will represent your avatar and username. Users can mint more than one NFT and select the one they want to serve as their profile. NFT holders can post and tip other people's posts. The posts with the most tips will appear first on their feed. You do not need to be a developer already to follow along with this tutorial. It is totally beginner friendly. I will explain all the technologies, data structures, and programming languages as they are introduced. Before we jump into setting up the project, let's get an overview of some key concepts like what a blockchain is and what NFTs are. We're also going to go over the different technologies we'll use to build out the application and how they all connect to each other. So let's jump straight into it. So what is a blockchain? You can think of a blockchain as a distributed ledger. Blockchains can be used to represent the transfer of value because once a transaction has been added to the blockchain, it can't be undone. Unlike traditional databases, it is decentralized and immutable, so no one has the power to tamper with the transaction records. They circumvent the need for trust. On the Ethereum blockchain, you can create these special programs that live on the blockchain called smart contracts. They allow you to exchange anything of value in a transparent, trustless, and secure manner according to the terms written into the code of the contract. Smart contracts are what power decentralized applications, or dApps for short. Some of the more popular types of dApps on the Ethereum blockchain include decentralized exchanges, crowdfunds, or digital banks that can issue loans, just to name a few. For this project, we will create a smart contract that will represent an NFT collection and the social network that the holders of the NFT can participate in. So you might be wondering, what is an NFT? Well, an NFT stands for a non-fungible token. The best way to explain what a non-fungible token is to compare it with a fungible token. A fungible token is an asset that can be interchanged for another within the same class. Cryptocurrency and dollars are examples of fungible assets. Each $1 bill that has ever been printed is worth the same amount, so it doesn't matter which dollar bill you own. The same can be said for all the Bitcoin that has ever been mined. However, with NFTs, it does matter which one you own because each NFT in a particular collection has unique content about it that makes their perceived value different. This content is usually an image or a GIF. In most cases, storing this content directly onto the blockchain is infeasible due to the blockchain's limited storage capacity. So as a workaround, this content, also referred to as metadata, is stored outside of the blockchain on a decentralized file storage system called IPFS. And the NFT smart contracts store a fixed length hash that points to where the metadata is located on IPFS. And in addition to storing the NFT metadata onto IPFS, we will also store each post made on our social media app on IPFS and store the hash that points to it inside of our smart contract. And once we have coded the smart contracts and have written tests against them, we will deploy them to a local blockchain. Then we will start building out the client-side portion of the application using the React.js framework, connecting it to the blockchain and the smart contracts we deployed to it. Now let's start installing the dependencies we need for the project. So first, we're going to install Node.js. This is a system dependency that allows us to execute our code in a JavaScript environment outside of the browser, and it allows us to install packages using Node Package Manager, which comes bundled with Node.js directly from our terminal. So it's a very important dependency, and it's a fundamental dependency, so that's why we're going to install it first. So I recommend installing the LTS version. So just by clicking this button and following the installation steps on the install wizard once it's been downloaded. And if you're not sure whether you have Node installed on your machine yet, go ahead and open up a terminal and type the following command, node-v, and then hit enter. And it should output the version of Node that you have installed. So I have version 17.0.1. And for this tutorial, I recommend installing any version of Node between 17.0.1 and this version to avoid any dependency issues. The next dependency we're going to need to install is Hardhat. This is a smart contract development framework. And what that is just essentially a set of tools that allow us to develop smart contracts, right, for Ethereum. So it comes with a Solidity compiler to allow us to write smart contracts in Solidity programming language, a test runner for writing JavaScript tests against our smart contracts, and we can spin up a local development blockchain with Hardhat, which we can use to deploy our smart contracts to and test them out. To install Hardhat, go ahead and open up a terminal window in the directory where you save your development projects. For me, that's in my development directory. It might be different for you. And once you're there, you're going to enter the following command. And once you're there, you're going to enter the following command. npm install /save dev Hardhat. And we're going to install a specific version of Hardhat for this tutorial to avoid any potential dependency issues. And that version is going to be 2.9.2. And then hit enter. Don't be alarmed if you see any warning messages from npm. As long as you don't see any error messages, then you know the installation was successful. The next dependency we need is the Metamask browser extension for Google Chrome. This will turn our browser into a crypto-compatible browser. So to install it, go ahead and click this download button. Then click Install Metamask for Chrome. Go through the installation steps. And then go to your settings. Then click Extension Settings. And then make sure that Metamask has been enabled. And you know it will have been enabled if you see a Fox icon at the top right-hand corner of your browser, like so. Now let's start coding out the project. So go ahead and click the link to the GitHub repo that contains the code solution for this project, right here, the Centra Twitter. And once you're there, go ahead and copy the link to it. Alrighty? Now go ahead and clone the starter kit branch by typing git clone /b starter code, and then paste in the repo link. Then we're going to give the project a name. I'm going to call it Decentra_Twitter, and then hit enter. All right, now go ahead and enter into that newly created project directory, like so. Alrighty. And first thing we're going to do is install the project-specific dependency using npm by typing npm install and then hit enter. Alrighty, and here's the starter kit code for the React app rendered out. And right now, there's nothing wired to this application. It's not connected to the blockchain in any way. And we have the nav bar up here. And right here is where we will display our Ethereum address connected to the app once we do connect the app to the blockchain. And we have instructions to where you can edit the source code of the client-side app right here. So now let's go ahead and open up the project in a text editor. So I'm going to go ahead and create a new terminal tab. So duplicate tab. And I'm going to open up the project in a text editor from my terminal. I'm going to open it up with VS Code. You can use whatever text editor you like, but I'm going to use VS Code for this tutorial. So I'm going to enter the command code space dot and then hit enter. Alrighty, and here's what's inside the project. Inside of this contracts directory contains the smart contract, the Centra Twitter that our front-end application will talk to, and it's written in the Solidity programming language. We also have a scripts directory, and inside of here we have a deploy.js script. So this is a script that when we run it will deploy this smart contract to a local development blockchain. And you could think of the word deploy as essentially meaning just putting smart contracts on the blockchain. That's all we're doing. And the source directory contains all the source code for our React app, the client-side portion that we displayed earlier. And the app.js file, this is where the source code of the app that we were previewing earlier is rendered. And then we have some tests right here. And this is where we're going to write the code for the JavaScript code rather to execute automated tests against our smart contract to ensure that it's behaving correctly. And it uses the Mocha testing framework and the Chai assertion library to execute the tests. And it uses the Ethers library as a library for blockchain interactions. It allows us to talk to Ethereum nodes from JavaScript environment. And then inside this hardhat.config file, we specify the version of the Solidity compiler we're going to be using to compile our smart contracts down into from the Solidity programming language to the machine readable code, which is bytecode. That's the code that the EVM compiler understands. And then we have this package.json file, which contains all of the project specific dependencies that we installed earlier using the npm install command. So for this project, we're going to use React Bootstrap to style the front end portion of our website. So we don't have to write a bunch of CSS code manually. It comes with a lot of templates that we can reference. We're also going to use React Router DOM dependency to allow us to route between a home page and a profile page for the app. And we're also going to use the IPFS HTTP client to store the metadata of the NFTs and the posts programmatically. And we're also going to use the OpenZeppelin smart contract library to reference a ERC 721 NFT standard contract inside of our Decentra Twitter smart contract. And OpenZeppelin, in case you're not familiar with it, is just a library of secure pre-made contracts. These are contracts that developers often use over and over again, and they're battle tested. You know that they're secure when you use them. So yeah. Alrighty, now that we've toured the project, let's go ahead and start coding out the Decentrate smart contract. So one thing I should mention quickly before we proceed is that when you're naming the Solidity file, there's a certain convention you need to follow, and that is the file name should start with a capital letter. And if the smart contract or the file name has multiple words, you need to capitalize the first letter of each of those words with no spaces. So yeah, let's proceed. So inside of here, we have the smart contract we've declared right here, and some imports, and then a pragma statement, and the license of the code. So in order for the Solidity compiler to not yell at you, you need to declare the license. And this pragma statement just tells the Solidity compiler the version of Solidity that we're going to use. So we're going to use version 0.8.0 and above. And we indicated that it's above by this caret symbol. And then we end every single line of code with semicolon in Solidity. And we also import the OpenZeppelin ERC721 URI storage from OpenZeppelin smart contract library. And then we go ahead and create the contract using the contract keyword, followed by the name of the contract, and then is followed by all of the smart contracts that our main contract will inherit. So we're going to inherit the ERC721 URI storage contract that we've imported up here. And then we've created a constructor function. So this is a special function that is called each time the contract is deployed to the blockchain, and it's called only once during the deployment phase. And since our contract is inheriting the ERC721 URI storage contract, this inherited contract has a constructor of its own. And in order for this contract to compile, we also need to call the constructor function on the inherited contract, and it takes in two arguments, and that is a name and a symbol, and that represents the name and the symbol of the NFT. So we pass that here to the ERC721 contract, like so. And then in curly braces, that is where the code of the constructor function will live. But because the constructor function for the Decentrate contract is not going to do anything, we're just going to leave it blank. We're just calling this constructor function in order to call the constructor function of the inherited contract. That's the way you call inherited constructor functions in Solidity. Alrighty, now let's go ahead and read the name and symbol of the contract, which we've initialized inside of this ERC721 constructor function. We set the name to Decentrate and the symbol of a Dapp. So let's read that. Now to do that, we need to open up the Hardhat console by typing npx hardhat console, and then we have to specify the network we want to use to interact with smart contract. So it's going to be localhost. Okay. And all the Hardhat console is just a JavaScript environment for interacting with the blockchain and any smart contract we have deployed to it. So let's first get a pointer, JavaScript pointer, to the Decentrate smart contract. So we could do that by saying const, and then name contract await, and then we're going to say ethers, and then get contract at method. Then we're going to pass the name of the contract. So it's going to be Decentra Twitter, right? Followed by the address of the contract, which we log to the console up here. So copy that and paste it between quotes like so. Okay. All right, that looks good. Now let's go ahead and hit enter. Hopefully it works. Okay, it says undefined, but let's type contract again, hit enter, and it should display the fetched contract. Sweet, so this giant contract object contains all the information about the contract, such as its ABI. Well, really, not all the information, just the information needed to interact with the contract from JavaScript environment. So it defines the set of all the functions that can be called externally right here. So let's go ahead and call this name function and this symbol function, which will fetch the name and symbol of the contract. So we could do that like so. Const name, right? Await and contract, followed by the name, parentheses. Okay. All right. Name, Decentra Tutor. Awesome. That's what we expect. Now let's do the same thing for the symbol. Await. Oh, and I should mention, I'm using this await keyword because whenever you're interacting with the blockchain, well, any function call rather to the blockchain is asynchronous. So what that means is that function calls return, rather than returning a value immediately, it returns a promise. And you need to use the await keyword to wait for the promise to resolve into a return value or an error message before you execute any other code that occurs afterwards, right? So if I were to say const symbol and let's say contract dot symbol like this would just return a promise. It wouldn't return the actual symbol of the smart contract. And I'm going to say that this is a let variable type. So I'm going to reassign this variable. So like this, and then I type symbol. As you can see, it returned just a promise. But if I use the await keyword, then it's going to return the actual value that was fetched from the blockchain. So, okay, syntax symbols already been declared. Oh, whoops. Let's remove the let, try that again. Okay, sweet. Here is the returned symbol from the smart contract, DAPP. Sweet. Now, really quickly before I continue, I should mention that Hardhat injects this ethers object inside of the Hardhat development environment. So that's how we were able to access it from the Hardhat console. And we're going to use this ethers object a lot when we're building out our test and connecting our client-side application to the blockchain. But for now, let's focus on coding out the Solidity portion of the app, so the actual smart contract code. And for each new feature that we implement into the smart contract, we're going to create an automated test for it right here to test out that feature. So we're going to build out the smart contract as we build out the test for it. So let's go ahead and get started. All right, so first things first, let's go ahead and define a couple of state variables. So we're going to have one variable that will keep track of the token count or the number of NFTs that have been minted, as well as the number of posts that have been created, so the post count. And the state variable in Solidity is essentially just the data that, so in Solidity, state variables is the data that is stored to the blockchain. And the only data that the smart contract can manipulate directly are those state variables, and when through the use of functions defined in the smart contract. And when these state variables are changing, when they're being updated by calling functions that do that in the smart contract, then the state of the blockchain is changing, and therefore it requires that the user who's calling those functions pays a gas fee. So that's how it works at a high level. So to define a state variable, you first have to explicitly state the data type of the variable. So it's going to be, for the token count, an unsigned integer, 256 bits in size. And the reason why we need to be explicit with the data type is that Solidity is a statically typed language, which means that once you declare a variable of a specific data type, you can't declare that variable as another data type. The data type has to remain persistent for a given variable. And we're also going to mark it as public so that this token count variable can be read outside of the smart contract. Okay. And then we're going to do something similar for the post count. Next, we're going to define our own custom data type for each post that is stored inside of the smart contract. So the way we do that is in Solidity is by using this thing called a struct. Okay, so we declare a struct by first using the struct keyword followed by the name of the struct, which will be post, and then curly braces. And inside the curly braces is where we define each data field of the struct. So we're going to have a data field of type UN256 to store the post ID. So the ID, which will correspond to an integer that allows us to identify each individual post. And then a string to store the hash of the post. So this hash will point to where the actual content of the post is stored on IPFS, because as I mentioned before, we're not storing the string of the post on the smart contract. We're just storing the hash of where it's stored on IPFS. And then we're going to have another field, UN256, to store the tip amount. So the total amount of tips that a post has received. And then we're going to, for the last field, store an address data type. I'm going to mark it as payable to store who the author of the post is. The address data type in Solidity is a special data type that allows us to store the address of accounts on the Ethereum blockchain. And these can be externally owned accounts or contract accounts. And we're going to mark this author field as payable because each time a post receives a tip, we want to pay the author of that post. So in order to do that, we need to mark it as payable. If we are paying the author in some other token, like for instance an ERC20 token, we don't need to mark it as payable. We just have to mark it addresses as payable if we want that address to receive Ether. Next, I'm going to define a mapping to store all the posts. Now you can think of a mapping as, if you're familiar with Python dictionaries, where you have a key value pair relationship. So in this instance, the key is a UN256, so an unsigned integer up to 256 bits large, and then the return value is a post. And the data type, and the return value is the post data type that we defined right here. And we're going to name it posts. So the way a mapping works is we essentially input a key and then it outputs the associated return value for that key. And in that way, we can store all of the posts and quickly look up any post based off its ID. Next, we're going to create a mapping that will store the profiles of each account. So it's a mapping that where the key is an address and it returns UN256, and this UN256 corresponds to the NFT ID for a particular address's profile, so the NFT that an address has selected to represent their profile. Next, let's go ahead and define a couple of events. So we're going to define an event for when a post has been created and for when a post has been tipped. And we're going to emit these events inside of a post created function and a post tipped function. Okay. So what does it mean when I say emit an event? Well, when we emit an event, we essentially log data to the blockchain. So this data will not be accessible from within the smart contract, right? But it's data that's nonetheless logged to the blockchain that external entities can query. So for the event created or event post created, the way we define it is we first use the event keyword followed by the name of the event. And then inside of parentheses, we define the data fields of the event separated by commas. And these data fields are just going to essentially be the same as the data fields for the struct. And we're going to do the same. We're going to emit a very similar event for the post tipped. The only difference is that the name of the event will be different. And I'll show you how we emit these events once we start building out the corresponding functions that actually creates posts and tips posts. Alrighty, now that we've defined all of the state variables and structs and events we need for the smart contract, let's start coding out the smart contract functions. So the first function we're going to create is a mint function. So when we call this function, it will create a new NFT and it's going to be minted for the address that calls the function. And we're going to pass to it as input the corresponding metadata of the NFT, which we'll assign as a token URI. And this will be a string. And whenever we're declaring a non-primitive data type inside of a function in Solidity, so that would include a string, bytes, or arrays, we need to explicitly state the memory location of said variable. So for string, we're specifying that it's memory, the data location's in memory. And what that means is that this variable only persists through the duration of this function call. So after this function call is done being executed, the variable token URI ceases to exist. The memory for it is used up. Now that is different from state variables, where the data location is storage. And for these state variables, the data is persistent because it's actually stored on the blockchain, right? It's not just stored in memory. The data is persistent. And we also have to specify the visibility of this function. So we say that it's external, which means that only outside accounts can call this function. And then we're going to specify a return type. We're going to say that it returns a uint256, and this value will correspond to the token count or the ID of the token that has been minted, which we're going to increment inside of the function body, like so. Okay. And once we've incremented the token count, which means we just increase its value by 1. Oh, and by the way, I should mention that in Solidity, whenever you declare a variable, but let's say you don't initialize it with a value yet, you just declare it, Solidity automatically initializes it with the default value of that variable's data type. So the default value of uint256 is 0. So even though we haven't manually initialized the token count or post count, Solidity automatically initializes it with 0. So Solidity does this automatically, right? So this token count, it's not undefined like it would be in JavaScript. So that's why we can increment it. It just starts at 0, and so we do ++, and then when we mint the first NFT, the token count will be set to 0 to start, and the ID of that token will be 1. And then we call the internal safe mint function, which will mint the NFT for us, or rather for the caller of this function, which we can reference using msg.sender global variable. And then we have to pass as a second argument the ID of the newly minted token, which will correspond to the incremented token count. And this safe mint internal function, this is provided to us through the inherited ERC 721 URI storage contract, which defines the NFT standard. Okay. And then we call another function, another internal function provided to us by the ERC 721 URI storage contract, which is the set token URI function. And for that, we pass in the NFT ID for the token URI we're setting. And then we pass in the actual content of the token URI. And then we go ahead and finish off the function by returning the token count. This will correspond to the, as I mentioned earlier, the ID of the newly minted token. Alrighty, and that completes the mint function. Now let's head on over to the JavaScript test for the smart contract and code out the test for the mint function. So to start things off, I'm going to paste in some boilerplate code. Now, what this code does is essentially exactly what we did inside of the Hardhat console. So if you remember, inside the Hardhat console, we got a instance of the Decentral Twitter contract, And from there, we call the name and the symbol functions on it to get the name and symbol that we initialized on the contract, right? Inside of the ERC 721 constructor, like so. And then we so we read those values and then we ensured that it equals the values that we expect right here. Now that's exactly what we're doing inside of this JavaScript test file, except it's just, when we run it, it does the test automatically, and it uses this expect. It uses from the chai assertion library the expect comparison. So it takes the resulting value that's returned, and then it compares it with the value that we expect it to have. And if there's a mismatch, if it doesn't equal the value that we expected, then the test fails. That's essentially how that works. And this before each hook, it basically executes all this code before each of the tests that are executed. And the tests are executed inside of the it statements. So, and this first test just describes the deployment of the contract, not necessarily the functionalities of it. And in the before each hook, we first we get the signers from the development accounts, right? So the first account we're gonna assign as the deployer, the second user 1, the third user 2, and then the rest of the users we're going to store in this users variable. And then we do that by calling the getSigners method on the ethers object. And then we get the contract factory to deploy the contract. So unlike in the Hardhat console, all we did was just instantiate a pointer to the contract, right? But inside of this test, we're actually deploying it, and from the returned deploy, and when we call the deploy method on the contract factory, it actually automatically returns a pointer to the contract. We don't have to instantiate it by like passing in the address of the contract and the name of the contract like we did in the Hardhat console. That's the only difference. And this line of code is basically the same code we use inside of the deploy script to deploy the Decentra Twitter contract. Okay, and then after that, user 1 mints an NFT, right? And we do that in the before each hook. And we pass in a URI, which we set just as a sample URI. And yeah, that's basically the gist of the boilerplate code. Now let's start writing the code that will test out the minting NFTs feature on the smart contract. So to do that, we're first going to describe minting NFTs and pass in an asynchronous callback. Inside of the callback is where we're going to pass in it runner, test runner, and it should track each minted NFTs. Pass in yet another callback. Inside this function callback is where we're going to actually execute the test, right? So first we're going to fetch the token count. So this function just reads the token count state variable, right, from the contract, and we expect it to equal to 1 because we've minted an NFT, just one NFT in this before each hook. And we expect that the balance of the user 1 address is equal to 1, right? And so this balance of function comes with the ERC 721 NFT standard that our smart contract inherits. And all it does is it takes as input an address of a particular account and then returns the number of NFTs that that particular account owns. And since we minted an NFT for user1 account, we should expect it to equal 1. And then we get the token, we read the token URI for the NFT number 1. And we should expect it to equal to the sample URI because that's what we set for when we were minting the first token. We passed in the URI as a URI for that token. And then user2 we test out the mint functionality when user2 mints an NFT, right? So we do that by calling the mint function on the Decentra Twitter contract, except this time the account that's going to be calling this function is not going to be user1. We're going to set it to user2, and the way we do that is by calling the .connect function on the contract, which will set the signer for the contract to that account, and we just have to pass in the signer object to the connect method. And then after that, we just basically read the same values that we did up here. So token count, balance of, the token URI, we expect token count to equal to 2, the balance of user2 to just be 1, and then the token URI for the second NFT to be minted to just equal the URI. Alrighty, now let's go ahead and run this test to make sure that we coded it out properly. So return to your terminal, and if you're in the Hardhat console, you can exit out of it by typing .exit and then hit enter. Okay, and now to run the deploy script, you enter the following command: npx hardhat run, and then actually no, it's going to be npx hardhat test. My bad. And then hit enter. Sweet, and all of the tests passed. Awesome. Now let's go ahead and implement the next function inside of our smart contract. And this function is we're going to call it the set profile function. And this will allow users who have minted multiple NFTs to select which NFT or not just minted multiple NFTs, but like just owns more than one NFT from the Decentra Twitter collection, to pick the NFT that they want to represent as their profile on the social media platform. So first we're going to name the function set profile, and it's going to accept a uint256. Will be an ID. This will represent the ID that the ID of the token that the user wants to represent as their profile. We're going to mark the visibility as public, which means that this function can be called from outside of the contract and from within the contract. And we're going to call this set profile function from inside of this mint contract, like so. And we're going to pass in for the ID and token count, and this will make it such that the last minted token for a user is going to be set to their profile for the social media platform automatically. And then inside this set profile function body, we're going to have this require statement, and the first input to the require statement is some condition that must be met, and followed by an error message that will be logged to the blockchain if the condition is not met. And if the condition is not met, then the entire function call will stop and revert, and any state changes made to the blockchain will be reset as well. So inside this require statement, we're going to check that the user who called this function actually owns the NFT that they're trying to set as their profile by calling this owner of function, which was provided to us by the ERC 721 URI source contract inherited by the Decentra Twitter contract. We pass in the ID, and this will return the owner of the NFT, that ID, And if an owner doesn't exist for it, it will throw an error, right? For IDs that are non-existent. And so we check that it's equal to the caller of this function. And after that validation is done, then we go ahead and update the profiles mapping. So we pass as a key the caller of the function, and then we set it to the ID passed into the function call. And that completes the set profile function. Now let's go ahead and test it out inside of the Decentra Twitter test. So first, we're going to describe setting profiles. And inside of this, for the second argument, we're going to pass a callback, asynchronous. Then we're going to test that it should allow users to select which NFT they own to represent their profile. So for the test, we first mint another NFT. User 1 mints another NFT. So now user 1 owns 2 NFTs. Then we check that the newly minted NFT is now set as their profile. We do that by calling the profiles function, which gives us access to the profiles mapping on the Decentra Twitter contract, passing as a key for it user 1's address, and we should expect that it will return the last minted NFT for user 1, which should be 2. That should be the idea of it. Then user 2, or rather user 1, sets the profile to the first minted NFT. So they call the set profile function directly, like so. And we pass in the token ID as 1. Then we expect when we fetch data from the profiles mapping, passing user 1 address to it, that we get the value of 1. And then we test a fail case. So we essentially just trigger try to trigger this require statement. So we do that when user 2 tries to set their profile to NFT number 2, which user 2 has not, in this test case, has not minted any NFTs of their own, so they don't own any NFTs. So they should not be able to set their profile to NFT number 2, because that is owned by user 1. So we call it, and then we expect it to be reverted with must own the NFT you want to select as your profile. Ready? Now let's go ahead and run the test. npx hardhat test, hit enter. Sweet. Now we know the setting profiles functionality works like we expect it to. So we're going to describe tipping posts, and it should allow users to tip posts and track each post's tip amount. And first, inside the test, we're going to upload a post. User 1 will upload a post, passing in the post hash that we define up here, the sample hash. And then we're going to get users 1 balance before their post gets tipped, their ether balance. And the way we do that is by calling the get balance method on the ethers provider. And we pass in the address of the balance, ether balance we want to get. So we want to get user 1's ether balance, so we pass that to it. And then we go ahead and create a variable to store the tip amount, and we're going to assign that to the result of calling the parse ether method on the ethers utility. And we're going to pass to it the ether value. And what this will do is it will convert ether into its smallest subdivision, which is way. And the way the conversion works is 1 ether is equal to 10 raised to the 18th way. Now, the reason why we're doing that is that you can't represent decimals in smart contracts. So as a workaround, you have to represent all ether values in terms of its smallest subdivision, right? Because you can't divide it any further, therefore you can't represent it as an integer value, just very large numbers. So yeah, basically smart contracts, they only understand values in terms of its smallest subdivision. So that's why we're converting it to weight. And then user 2 is going to tip user 1's post. And the way we do that is by calling the tip post owner and connecting the Decentra Twitter contract to user 2. And then pass in the post ID, which is going to be 1. And then user 2 is going to send some ether with this function call. And the way we specify that ether amount is by passing in to the last argument to this function metadata, and that metadata will be contained within an object like so, and the value property of the object is where we specify the ether that we're sending with the function call, which we're going to set to tip amount. And then we expect that the function call emits a post tipped event and emits it with the following arguments. For the ID, we expect it to equal 1, the post hash that we defined up here, and the tip amount to equal this tip amount, and the author to be the user 1's address. Okay. Then we check that the tip amount has been updated from the struct. So we get the post struct from the post mapping, passing in the post ID. And once we have it, we check that the tip amount field on the post is equal to the tip amount that we set up here. Then we check that user 1 received funds, or rather received the tip amount. And the way we do that is by first fetching the final author balance, by calling the get balance method on the ethers provider. And then we expect that the final author's balance is equal to the initial author balance plus the tip amount. Now, the reason why we're not just using JavaScript's right plus sign operator to add these two values together is that JavaScript does a poor job at doing arithmetic with very, very large numbers. There's usually some precision error involved with that. So as a workaround, the values that are returned from the get balance method, these are special ether big number values, or rather objects. And these objects come with special methods that allow you to do arithmetic of other ether big numbers safely. So that's what we are doing here. In order to add the initial author balance to the tip amount safely, which both of these values are ether big numbers, we have to call the add method on the one of the values and then pass in the other value that we're adding to it. And then we check the first fail case. So user 2 will try to tip a post that does not exist, and we expect it to be reverted with invalid post ID. I'm going to pass 2, which only one post has been created so far, so we should expect it to be reverted. Then we check the second fail case, which is when the author of a post tries to tip their own post. So user 1, the author of the first post, tries to tip their own post, and we should expect it to be reverted with cannot tip your own post. All right, and that completes the tipping post test. Now let's go ahead and run it. Okay, npx hardhat test. Sweet, and all of the tests passed. Now to finish off the Decentra Twitter smart contract, we're going to create 2 more functions. These are going to fetch data from our smart contract. They're not going to write any data. So they're not going to modify any of these state variables. So they're not going to cost any gas to call. We're going to have one function that will get all of the posts that have been created, and then another function that will get all of the users' NFTs. And when we're building out our client-side portion of the application, we're going to call this get all posts function when we're building out specifically the home component, which displays the user's feed. And this will fetch all the posts within a single function call. And when we're calling and when we're building out the profile page, we're going to need to call this get my NFTs function in order to display all of the users' NFTs that they have available to choose as their profile. So for the get all post function, we're going to mark it as the visibility is external. Say that it is a view function, which means that it only reads state variables and doesn't modify them. And then we're going to specify what's returned. And we're going to return an array of type post. The data location is going to be memory, and the name of the returned variable is going to be underscore posts. And then we're going to assign the in-memory posts array to a new in-memory array of a fixed length. And the way we initialize a new in-memory array is with the new keyword, followed by the data type of the array, and then brackets, followed by parentheses. And inside the parentheses is where we pass in the length of the in-memory array. And that's because in-memory arrays have to be a fixed length. They can't be of dynamic length. And we're going to pass in the post count. Then we're going to loop through the posts array, assigning for each index the corresponding value returned from the posts a mapping up here. And we're going to set it the current index, so I plus 1. And this is because the posts count for each post starts at 1 all the way to the current post count. And the way this for loop iterates is that it starts from 0 all the way to the second to last post count. So therefore we have to shift it up by 1 in the post mapping. So that's why we're doing I plus 1. Now, the first thing we need to do when building out our client-side application is we need to connect it to the blockchain. Now, we can't connect it directly to the blockchain. We need to connect it using this thing called a provider. Okay? So the way it works is that Google Chrome, our browser, will connect directly to the blockchain by way of Metamask. And the way we're going to configure that is that we're first going to add the local development blockchain running on our computer, the Hardhat blockchain, as a list of available networks on Metamask, right? And then once we do that, we're going to connect the private keys of the development accounts from there, we're going to import the private keys of the development accounts into Metamask. And once we do that, we will have established a direct connection from our browser to the blockchain. And once that connection has been established, then we can connect our client-side application to the blockchain through the browser. So the browser will act as a provider. Now, previously, when we were interacting with the blockchain inside of our Hardhat development environment, so when we were writing automated tests that interact with smart contracts on the blockchain when we were interacting with the blockchain inside of Hardhat console. In all of those instances, Hardhat provided the provider automatically. We didn't have to set it up, right? But when we're building out the client-side application, this React app is outside of the Hardhat development environment. So because of that, we have to manually set up our own provider. So let's go ahead and start by adding the Hardhat network to the list of available networks inside of Metamask. You can do that by clicking this icon at the top right of your Metamask to the left of this circle profile. And then go down, once you've clicked it, go ahead and go down to add network, that button. And then you're going to fill out all of these fields with this information. And once you've done that, make sure that you've selected the Hardhat network in your MetaMask. And now let's go ahead and import the private keys of the accounts in our development blockchain into MetaMask. To do that, go back to your terminal and go to the tab where you have your development blockchain running. And then go ahead and copy the private key of the first account, so account number 0, like so. And then go to your MetaMask, click the circle icon, hit import account, and then paste in the private key of that development account, and then hit import. Sweet. And now we've imported the first development account, the deployer account, in our development blockchain into MetaMask, and that will allow us to sign transactions on behalf of this account on our app, which is pretty cool. Now, we also want to be able to sign transactions from other accounts. So to do that, go ahead and import the development account number 1 below it, as well as number 2. Sweet. Now that we've connected our browser to the blockchain and are able to sign Ethereum transactions using the first 3 development accounts in our development blockchain, let's pivot focus to the client-side code. Now let's start modifying this code and creating the functions we need to connect our client-side application to the blockchain. So to start things off, I'm going to paste in some boilerplate HTML and CSS code, as well as some imports. So the reason why I'm doing this is that the main focus of this tutorial is how to connect client-side application to the blockchain, how to interact with the client-side application with the blockchain specifically, not the design aspect of the app like the HTML and CSS. If you'd like to know more about what this HTML and CSS code does, how it's configured, you can check out the NFT marketplace video I did. I explain all of this code more in depth there. And so the first import we have here is the React Router DOM dependency. We're importing link, browser router, routes, and this allows us to make our app multi-page and load different pages depending on the URL path. And then we have a use state hook, which we're going to use to set the state of our application. Then we import the ethers library. And then we also import the ABI of the smart contract, as well as its address. We're going to need both of these pieces of information to create a JavaScript pointer we're going to need both of these pieces of information to create a JavaScript pointer of our Decentrtwitter smart contract. We're also going to import some components from React Bootstrap to make our UI look pretty. So container, button, nav bar, spinner. We're also going to import the Dapp University logo and the app.css. That's where all the styles will go. Now let's go ahead and write the Web3 handler function, which will connect our wallet to the application. And it's going to be fired whenever the user presses the connect wallet button in the nav bar. So first things first, we're going to define the state of our app component. So we're going to have a piece of loading state to store the account, and the Decentra Twitter contract. So we need a piece of state to store when the app is loading or not, because we don't want to display the contents of the application when blockchain data is being fetched. So we're going to set loading to true initially. And down here, we have this ternary operator. So it checks if loading is true, then it displays this loading page. And if it's false, then it displays the contents of the application. And then we also have an account, which we'll use to store the address of the account that's connected to our application. We're also going to store a pointer to the smart contract, like so. And the first thing that's outputted from this useState hook is a variable that we can use to reference this piece of state, right? And then the second element is a setter function, which we can pass a value to update the stateful variable. And then we pass the useState hook itself the initial value of each piece of state. So before the value is set using the setter function, this is the value that it will be assigned to. And then for the Web3 handler function, we're first going to get the accounts that are inside of our Metamask wallet that are connected to the app. And the way we do that is by calling window.ethereum request, passing in the method eth_request accounts, returns an array of all the Metamask accounts connected to the app. And the first account in that array represents the account that the user is interfacing the app with. So we're going to pass that to the setAccount setter function. And then we're going to set up some event listeners for MetaMask. The first one is going to be the chain changed. So this is a callback function right here that will get triggered whenever the user changes the network that they're connected to on MetaMask. And then when that happens, we're going to reload the application. So essentially click the refresh button. And then we're going to have another listener for when the user changes their account. And when that happens, we're going to set loading to true. And then we're going to call back into this Web3 handler function to reload the accounts and the smart contract. And then we're going to get a provider object from MetaMask. And the way we do that is we use a new ethers keyword, .providers, and then we have to specify the type of provider. And the type of provider that MetaMask provides is called a Web3 provider. And the way we instantiate it is by passing in the window.ethereum object that MetaMask injects into browser, like so. And this is globally accessible inside of our client. And once we've instantiated the provider, then we can get the signer from the provider by calling the getSigner method on the provider. And you can think of a signer as just an abstraction of an Ethereum account that you can use to sign transactions. And this will return the signer for the account that's connected to the app. So this account right here that we pass to the set account method. And then we're going to pass the signer to this function that we have yet to define, which is a load contract function. So let's define it. The load contract function will accept as an argument a signer. And then we're going to get deployed copy of the Decentralized Twitter contract by calling the contract method on the ethers object and passing to it the address of the contract as well as ABI and the signer, which we passed in here. And then we're going to update the contract state as well as the loading state to false. Awesome. Now let's take a quick preview of what our app looks like so far. So here it is. We have the navbar rendered out with the connect wall button, the 2 navigation links, Decentralized Twitter title, and we have a loading page with the spinner rendered out, awaiting Metamask connection. So if we click the home link, navigates us to the base URL path, and then if we click profile navigation link, it should navigate us to the /profile URL path. Sweet. And then if we click the connect wall button, it should connect this account to our application. Let's actually switch off to this one, this account. So let's do that. Awesome. And then if we switch accounts from Metamask, it should automatically connect that account that we switched to the app. So let's do that for account 3. Awesome. Now that we've built out the app.js component, let's focus on building out the home component. So this is the component that will allow us to create new posts and view posts, as well as tip the post that we can view. So let's go ahead and start building it out. So let's go ahead and create a new file inside of this source directory for the home component. We're going to name it home.js. So to speed things along, I'm going to paste in some boilerplate code inside this home.js file. So here for the home component, we're going to pass the contract and the account, which we fetched from the app.js component. We're going to pass these 2 pieces of app.js state to it. And then we're going to, inside the home component, we're going to load a piece of loading state. And if the loading is true, then we're going to render out a loading page. And if not, then we're going to render out the contents of the home component. And we're also going to import IPFS HTTP client because we're going to need this to upload the posts that users make to IPFS. So first things first, let's create a function that loads all of the posts that have ever been created. So it'll look like this. And we're also going to add another piece of state, has profile, to save whether the account connected to the app has an NFT or not. So that's the first thing we're going to check for inside of this load posts function. So the way we check for that is we call the balance of function on the contract, and we're going to pass in the account property of the home component to it. And then that will return the number of NFTs that account owns. And if that number is greater than 0, then we're going to set the has profile state to true. And if not, back to false. And next, we're going to call the get all posts function on the contract. And then we're going to map through all of the results like so. in order to fetch the metadata of each post and the profile metadata of the author of each post. And because we're passing an asynchronous callback function to the map method, the results.map is going to fire each of these asynchronous calls one after the other without waiting for each promise that's returned from the async function call to resolve before firing the next one. So it's going to fire all of them in parallel. So we have to cast that map in a promise.all, which will basically return, the promise.all will turn a promise that will resolve once all of the asynchronous callbacks that have been fired in parallel all finally resolve, or until the first one that doesn't resolve returns an error. In that case, the promise.all will return an error message. And once it resolves, then it will finally return the resulting mapped through results array, which we'll assign to a post variable. So first, we use the hash to fetch the post metadata stored on IPFS, like so. And then we're going to get the author's NFT profile by calling the profiles function on contract, passing in the author of the current post. And then we're going to get the URL, the URI URL, the NFT profile, calling the token URI function, passing in the NFT ID that we fetched. And then we're going to fetch the NFT profile metadata using JavaScript fetch API, like we did for when we fetched the post metadata, passing in the URI, the return URI. And then we're going to define an author object. So the author consists of 3 fields of information, which is the address of the author, as well as the 2 pieces of metadata, which includes the author's username. So we get that from the metadata profile, which we fetched right here, username, and then the metadata profile avatar field, which we got up here. And these 2 pieces of information are what compose the NFT profile of the author. And then we define a post object, which includes the ID of the post, the actual content of the post we stored on IPFS, we get that from the metadata post, and the tip amount, which we get directly from the smart contract, as well as the author object that we defined right here. And then we return that post. And once we have fetched the metadata of each post, as well as the metadata of the author of each post, and added that all to a post object, we can now sort the posts from most tipped to least tipped, like so, using the sort method. And then we can update the posts state as well as the loading state. Oh, and let's go ahead and define the posts state using the use state hook up here, like so. Awesome, and that completes the load post function. Now, we want to make it such that this load post function is triggered each time the home component is mounted to the DOM. And the home component is mounted to the DOM each time the home component, each time someone clicks the refresh page and they're on the home component, so they click the home link, or whenever someone switches from being on the profile page to clicking the home link and then loading the home page. So in those 2 instances, that's when the home component is mounted. So how can we code that out? Well, we can use the use effect hook to accomplish that. So the use effect hook accepts a callback function, which is triggered each time the component updates, which happens when the state changes or the component is mounted. Now we only want to call the load posts function in the case when as I mentioned, the home component is mounted to the DOM. And we can use an if statement that checks if the post's state is set to null, then in that instance we'll load the posts. Because we know that if this home component is being mounted for the first time, this post value will always be set to null. Awesome, and that completes all of the blockchain interaction functions we need for this home component. Now let's focus on building out the user interface using HTML and CSS inside of this return statement. So first things first, we're going to render out the post form. So first, we're going to write some embedded JavaScript between these HTML elements. And the way we do that by using curly braces. So that's where we write the JavaScript code. So we're going to check if has profile is true. And if that's the case, we're going to render out the post form. And if not, then we're going to render must own an NFT to post. And this is because to use the social media platform, you must hold an NFT. And each time there is a change to the form input, we're going to update the post with the value inputted. And when the user clicks the upload post button, we'll trigger the upload post function. All right, and then below the posts form, we're going to render the posts. And first we're going to check that the post.length is greater than 0. And if not, then we're going to render no posts yet header. But if the post length is greater than 0, then we're going to map through the posts. And for each post, we're going to render out a card. And inside the card header, we're going to have an image that's going to display the post author's avatar, as well as the post author's username to the left, and then the post author's Ethereum address to the right. And then for the card body, we're going to have a card title, going to display the content of the post. And then for the card footer, we're going to display the tip amount, and we're going to convert the post's tip amount from Way to Ether using Ether's utils format Ether method. And then we're going to check if this really should be account. If the account connected to the app matches the author of the post, so the address of the author, or if the account doesn't have a profile, then we're going to return null. But if both of these cases are false, then we're going to render a on-click. But if both of these cases are false, we're going to render a button that allows users to tip the post. So basically what this condition means is that you can only tip posts if you have an NFT, and the post that you're trying to tip, you are not the author of. Awesome. And that completes the home component. Now let's wire it up inside of our app component. Let's first import it like so. And then we're going to add the home component to the home path like so. Passing in the contract, the prop, as well as the account like so. Awesome. Now let's take a preview of our app, see if it's working like we expect it to. Okay. Connect wallet. All right. Must own an NFT to post. No post yet. This is what we should expect because obviously we haven't created a NFT yet, so we can't make any posts. Once we finish building out the profile and we create a profile for ourselves, then we can access the post form, create a post, and then we'll see that post in the feed. So let's go ahead and start building out the profile then. So we can do that. So let's go to this source directory side of it, create a new file. We're going to call it profile.js. So like with the home component, I'm going to paste in some boilerplate code. To start, we're going to use the IPFS client yet again to store the metadata of the NFT profile that users can create from the profile component. So first, let's create a function that loads all of the user's NFTs. We're going to call it load my NFTs. And first, inside the function body, we're going to get the user's NFT IDs, so all the IDs of the NFTs that they own, by calling the get my NFTs function on the contract. And then we're going to fetch the metadata of each NFT and add that to NFT object by mapping through the results. So inside the function of the callback, inside the map, we're going to get the URI URL of the NFT, calling the token URI function on the contract, passing in the ID of the NFT, the current NFT rather. Then we're going to fetch the NFT metadata by passing in the URI to the JavaScript fetch API. That'll return a response, and then we'll get the JSON representation of that response, calling the JSON method on the response, wait for it to resolve, and then we will return the NFT object, which will include the ID of the NFT we got from the contract, and then the metadata of the NFT we got from IPFS, which includes the username, metadata username, the metadata avatar, and then we're going to set the NFTs, and then we're going to call the get profile function, passing in the NFTs, which is a function that we have yet to define, and this function will filter through the NFTs to determine which one is representative of the user's profile. So for the get profile function, we're first going to get the address of the account that's connected to the app by calling the get address method on the signer of the contract. And then we're going to get the account's NFT profile and the ID that corresponds to it by calling the profiles method on the contract, passing in the address. And then we're going to use a find method on the NFTs array to find the NFT that matches the returned ID in the array. And then we're going to set that to a profile variable. Then we're going to set the profile state with that profile variable, which we will need to define up here like so. And then we're going to set loading to false, because that is all of the initial blockchain data we need to fetch when this profile component mounts. So now let's add the use effect hook that will fire this load my NFTs function when the profile component mounts. It'll look like this. And inside the use effect callback, we're going to check if NFTs is a falsy value, which indicates that the component is mounting. Then we're going to call load my NFTs. Awesome. Now we just need to add 3 more functions to this home component, starting with a function that uploads the image that the user wants to set as their avatar for the NFT profile that they're minting. And then another function that interacts with the blockchain to mint the profile NFT. And then we'll have another function that writes data to the blockchain, which will allow users to switch their profile. And so basically select a different NFT that they own to represent their profile. This upload to IPFS function will accept an event argument, and it will get fired whenever there's a change in the image input for the NFT profile form. So first, we're going to prevent the default behavior when uploading images. And then we're going to select the file, the image file from the event.target. And that's the image file will be represented by the first element in the return files array. And then we're going to check if the data type of the file is not undefined, which indicates that the user actually inputted a file to the file input field and didn't just like upload something that didn't exist. And then we're going to create a try catch hook, and we're going to, inside the try hook, add the file to IPFS, and then we're going to set the avatar by taking the returned result, getting the path of that result, and then sending it to the HTTPS IPFS infura.io IPFS URL. And then in the catch hook, we will log an error to the console if there is one. Actually, we should probably just set this as a window alert. And that completes the upload to IPFS function. And for the mint profile function, this function will get triggered whenever the button to submit the NFT profile form has been pressed. So first, inside the function, we're going to do some basic form validation, check that the avatar username exists, and if not, we're going to return. And then we're going to have a try catch block. So inside the try block, we're first going to add the avatar and username to IPFS. And before we add it, we're going to stringify it, turning it into a JSON object, the avatar and username. And we're going to set the loading to true. Then we're going to call the mint function on the contract, passing in the token URI or the metadata. And then we're going to wait for the transaction receipt to return. And then we're going to update the NFTs on the page with the newly minted NFT by calling the load my NFTs function. And then we're going to have a catch block that alerts the user of IPFS URI upload error. Alrighty, and that completes the mint profile function. Now let's focus on the last function inside this component, the switch profile function. It accepts as input an NFT. And then first we set the loading to true. And then we're going to call the set profile function on the contract, passing in the ID of the NFT. And we're going to wait for the transaction receipt to be returned. And then we're going to call the get profile function. And that will update the profile component with the newly selected profile. Awesome, and that completes all the JavaScript functions we need for this profile component. Now let's build out the user interface of it. So at the top of the profile component, we're going to render out the user's NFT profile. First, we're going to check if the user actually has a profile, and if so, then we're going to display the profile's username at the top, and then below it, the profile avatar. And if the user doesn't have a profile, then we're going to display the following message: no NFT profile, please create one, a header format. And then below the profile, we're going to render out a form that allows users to mint a new NFT to represent their profile. So this form at the top, we're going to have a input of type file that allows users to upload an image file to represent their NFT avatar. And then when there's a change to the input, we're going to trigger the upload to IPFS function. And then below that, we're going to have a basic text field, input field. And whenever that changes, we're going to set the username to the value inputted into the field. And then below those two inputs, we're going to have a button, a mint NFT profile, the title of it. And whenever it's clicked, we're going to trigger the mint profile function. And below the mint NFT profile form, where we're going to render all of the other NFTs that the user owns that the user doesn't have represented as their profile. So basically, we're going to map through the NFTs array. We're first going to check if the NFT ID is equal to the profile ID, and if so, we're just going to return null for that. But if the NFT is not their profile, then we're going to render it out using a card. And at the top, we're going to have the image of the NFT, so the avatar, and then the card title, where we're going to display the username of the NFT wrapped in card body. And then inside the footer, where we're going to have a button set as profile button that when clicked, we'll call the switch profile function. And then we're going to pass in the current NFT to it. Oh, and I almost forgot, we need to add the avatar and username to our state as well. Awesome, and now we have completed the final component of our app, the profile component. Now all we have left to do, coding-wise, is just import the profile component in our app.js, and then add it as an element to the profile path, like so. Sweet. Now let's take a look at the completed version of the application. Test out all the features, make sure everything is working as it should. So let's connect to wallet. Sweet. We see this is the profile page. No NFT profile, please create one. And we have the mint NFT profile form. Let's go ahead and mint one. Let's choose Dove mint NFT profile. Okay. Confirm the transaction. Sweet. And here is our NFT profile displayed. Awesome. Now let's go ahead and create another NFT profile. So sword. Whoops. Okay, mint NFT profile. Hopefully it will display below the form. Awesome. And as you can see, the most recently minted NFT profile is set as the latest profile. So if we want to switch back to the Dove to represent our profile, we could do so by clicking set as profile. Click confirm. Sweet, and it switched. Now if we go back to the home component, now that we actually own an NFT, we should be able to participate in the social media. So we should be able to, awesome, we can now write our own post. Do that. This is so cool. Create a post. Hopefully it shows up in our feed. Awesome. Sweet. This is so cool. Tip amount is 0. That's great. Oh, but I've already noticed a bug. This tip for 0.1 ETH button should not be displayed because we shouldn't be allowed to tip our own posts. So let's see if we can go back to the source code and fix that. So home component. Okay. So the error is right here. So this is where we render out the tip button. We're only supposed to render it out if the account does not equal post.author and it does not, and the user has a profile. So the issue is right here. So clearly the account should equal post.author.address for this post, but it's not. Don't know why that is. Let me see. Instead of using the past in account, we just get the address of the account connected to the app from the contract and then save that address to the state. So let's try that. We'll do const address equal to contract.signer.address. Okay. Actually, it's going to be get address. Okay. And then we'll create a piece of state for the address. We'll just store that. Okay. Say address set address. Alrighty. Then we're going to set the address with the fetched address from the getAddress method. Okay. All right, and then we're going to replace count down here with address. Oh, and then we also need to make sure that we are using the await keyword to get the address because this is an asynchronous function call. Alrighty, now let's go ahead and see if that fixes the issue. And sweet, problem solved. The tip button has been removed. Awesome. Now let's see if the post author's avatar and username changes whenever they switch to a different profile. So set as profile, confirm. Alrighty, see if it updates. Awesome. Now let's go ahead and switch to a different account. Okay. Let's mint an NFT for this one. Do pizza. Pizza's username. Mint NFT profile. Confirm. Sweet. Now let's go back to home. Awesome. So now we can upload posts and we can tip other people's posts. So let's go ahead and tip this post. See what happens. Tip. Okay. Awesome. The tip amount increased by 0.1 ETH. Now I'm going to upload my own post. So, wow, this is almost like Twitter. And then post it. Confirm. Sweet. Now let's switch back to the other account. And now I'm going to tip this post twice to where the tip amount is 0.2 ETH. And I want to see if my feed updates such that this post made by the pizza goes above sword. So let's do that. All right. Tip, right? Updates. All right, let's see if the pizza post goes above the sword post. Awesome. Alrighty, and that's it, everyone. We've built a Web 3.0 version of Twitter, whereby you need an NFT to participate. You should really give yourself a huge pat on the back. You have written your own smart contract and Solidity programming language. You deployed it to the blockchain. You wrote automated JavaScript tests for it to ensure that it behaved exactly how you wanted it to, and you wrote a client-side application that interacts with the blockchain and the smart contract deployed to it using the React.js framework. And we also learned how to upload NFT metadata to IPFS. So yeah, this is a scalable, decentralized social media application that allows users to create their own profile via minting an NFT, and they can tip posts that they like, and their feed is organized such that the post with the most tips appear first. And so if you want to take this application to the next step, there's a ton of things you could do to it. You could, for instance, add a feature that allows users to upload an image as well as text with each post. You could also add a feature that allows users to follow specific accounts. So as always, I would appreciate it if you smash the like button down below so this video can get recommended to more people interested in learning about blockchain development. And if you're eager to learn more, interested in blockchain development as a career, head on over to dappuniversity.com/bootcamp to get started today. All right, that's all I've got for today's coding tutorial. Until next time, thanks for watching Dapp University.